Hello, I'm David Anthony, Evangelist for West Coast Technology Solutions Division. And today I'm going to be going through part 1 of Server Storage Fundamentals. This section will include server, cloud, and shared storage. Part 2 will cover virtualization, hyperconverged infrastructure, and backup. While the picture on the screen shows a mountain to be climbed, this will start off very gently and gradually build up, with the more advanced topics being covered in the second part. But by then, I'm confident that you will understand the fundamentals and so understand those hardest sections. Now, selling a server, storage, whatever, is just the same as selling a laptop. Reason I'm saying that is they are all computers that contain the same elements, just in different quantities with different capacities, let's say. But if you can understand and talk about a laptop, there's no reason why you shouldn't be able to talk about infrastructures and servers. So the same thing goes for laptops, mobile phones, PCs, gaming or otherwise, smart watches, Kindle Fire Sticks, earbuds, everything. They are all computers and they all contain the same fundamental elements as a server. So, what are those elements? The central part of it is the CPU, the central processing unit, the processor, or the computer in effect. This is what does the calculations. You're no doubt familiar with the brands of Intel and AMD that make server processors. This is the beating heart of all computers, the CPU. What it does is it does a lot of simple calculations, either arithmetic or logic calculations, but it does so many of them that the end result can seem like magic. Creating Netflix, talking to a AI chatbot and it talking back to you, everything the same. All is done through lots of simple calculations, but repeated. Okay. So, how many calculations are we talking about? How many processes are we talking about? That is indicated on a server bill of materials by the gigahertz symbol. You will see 2.6, 3 gigahertz on a server bill of materials. That means how many calculations per second that processor will do. And that is, gigahertz is a billion calculations per second. It's the SI unit for frequency. So 2.6 gigahertz is 2.6 billion calculations every single second that processor will do. Hence why these computers can do things that seem incredible, but it's building up to lots and lots of simple arithmetic or logic calculations. Another phrase you will see on a bill of materials is how many cores that processor has. And this is because whilst the actual physical size of the processor, seen here, has remained the same for several years now, the technology that it takes to make this has actually got smaller and smaller and smaller. So now, NVIDIA, Intel, AMD, Intel and AMD specifically in this case with CPUs, we'll come on to GPUs later, but CPUs, Intel and AMD are able to make their processors significantly smaller. So within this one block, they can now put in multiple processors within that one physical block that is the same size, and those are called cores. So you'll see on your laptop maybe a 4-core processor. With servers, you will see anything from 24, 48 all the way up to about 128 cores. So that means that physical processor actually contains 128 cores. Okay? So if it's a 64-core processor and we have got 2 gigahertz, that means that we've actually got 64 processors all doing 2 billion calculations per second. Or in other words, we have got 128 billion calculations happening a second. So you can see with a server, you can get a lot more performance. Now, whilst the processor does the calculations, it has to get the data from somewhere, and when it's done the calculations, it has to put the resulting data somewhere as well. And that place for storing data is called memory. It's known as RAM for random access memory, or DRAM, dynamic random access memory, but we don't need to worry about that. This is just memory, and you get these memory sticks, as we can see here. These are the chips where the data is stored, and you will get a number of these memory sticks in a server. And the way it works is very much like a child doing a maths test. The question is written down on the paper. The paper in this case would be equivalent of the memory, so the calculation is written there. The child takes that sum, or that equation, into their head where they do the calculation. Once they've done that calculation in their head, they then write down the result back onto the paper, back onto the memory. And so the processor works in exactly the same way. How much data can it hold is dictated by gigabytes. A gigabyte is 8 billion bits of data, ones or zeros, because computers use binary maths as opposed to decimal maths, but a bit is a piece of data, and a byte is 8 pieces of data. So a gigabyte is 1 or 8 billion pieces of data. Okay, all very well. But the only problem here is this is very fast, incredibly fast. So when you write down the result of that sum onto here, it's written down very quickly. When the processor is reading the equation, if you like, that needs to be done, it can read it very quickly because memory is very fast. But its downside is that if the power plug is pulled out of the server, or out of the battery is taken out of the laptop or whatever, all the data in here would be lost. It requires continuous power for that data to be kept active on that memory. And this is why, if you are trying to turn off a laptop quickly and you're going to just X out of an application, you may get a notification bar coming up and saying, please save this data before closing. And that would mean that the data is still held here, so if the power is taken away, then all of that data is lost. So we need another medium to be able to put data that will stay there when there is no power, and that we call storage. Storage comes in a number of different types, of media, all of which are this permanent storage. They are slower than memory, so we still need the memory. The processor couldn't just be communicating with the storage. The storage itself would be too slow. But 3 different types of storage media that have developed over the years, getting faster and faster with each one. The oldest and still in use is tape, which is a bit like on cassette tape. I'll use the allegory for music all the way through here. Like a cassette tape. Cassette tapes now would be very cheap. Tape drives are very cheap, but they're very slow, because in order to get to the right bit of data, it's going to be somewhere in the big spool of tape, and that's got to be forwarded through or wound back to find where that piece is. So that's going to take seconds, if not minutes, to get there, which is just way too slow for most application tasks today. But tape is still used for archiving data, things like emails. If a company needs to keep emails for 5 years for legal reasons, they will typically store that sort of data on tape, and that would be called archive. The next storage media that came along was hard disk drives. Very similar in music terms to CDs. You've got a disk and the data is encoded magnetically onto that disk. That disk spins around, and then this armature will move along to find the sector where the required data is, so that data can then be sent to the memory so that the processor can access it from the memory. Much faster than tape, but still slow by comparison because it's got this moving part, this armature, which slows things down. So in time, there was SSDs. Flash was created, which is all done via electricity. There's no moving parts, hence solid in the solid state drive, and it will actually be 50 times as fast as hard disk drives, but obviously more expensive as well. So from a storage point of view, you would ideally want to put all SSDs or all flash drives into the server. However, maybe from a cost consideration point of view, you would only put certain things on there, like the server operating system and the applications, and say the application data itself would be put onto hard disk drives. That data that isn't going to be regularly requested by the processor. So the way it works is whatever data is going to be used is copied into the RAM, so that into the memory, so that the processor can quickly access that data from the memory. And with storage, we are talking about terabytes as opposed to gigabytes. Terabyte is 1,000 gigabytes, so 1 trillion bits of data or bytes of data, as opposed to 1 billion with gigabytes. Okay. Another thing that is included in all computers, be they servers, laptops, PCs, phones, smartwatches, whatever, is a input-output device. How the data is got onto the device and how it gets off the device in the first place. Servers, we are talking about Ethernet cable, Cat5, Category 5 cable, that is then plugged into the server, and data gets into and out of the server by going along that cable, modulated onto electricity. in the case of smartphones and laptops will do Ethernet cable, but they also, like smartphones, have wireless communication. So wireless communication is, as opposed to sending the data across copper wires via electricity, it's sent across via radio waves. Okay, so that's input output. And these days, over the last few years, we also have more and more GPUs, or rather we have processors that are being used for artificial intelligence. In certain laptops and PCs, over the years we've had GPUs, graphics processors, for things like gaming. But this has come very much more to the fore in these early days of AI, because it is now understood that these types of processor are really effective also for artificial intelligence. So what is the difference between a graphics processor unit and the CPU, the central processing unit? Other than the size, it's how they work. So the server processor could have, say, 24 cores, each one of those cores doing processes, but those processes are done sequentially. So each core will only do one process, one calculation at a time. Whereas the GPU does simpler calculations, but it does a whole lot of them at the same time in parallel. It will have also thousands of cores, and it will do all its calculations at the same time. So they're simpler, but a hell of a lot more of them are done per second. And that is the way that artificial intelligence applications work, by lots and lots of much more simple calculations, all to do with comparisons and things like that, which are done at the same time. So a computer, a server running an AI application will still have CPUs to manage everything, but the grunt work of the calculations will be done by these GPUs, of which currently by far and away the leading brand name of this is NVIDIA. Okay, so what is the difference then between these client devices and a server? So client devices, typically you're only having one person using these at a time, but they will usually have multiple applications sitting on them, just like with a phone, like with our laptops, multiple applications. But unless someone's looking over your shoulder, say, it's just one person uses this client device at a time, as opposed to a server, which traditionally, and still kind of, something I'll cover more when we get into virtualization in the next video, is a single application, sits on the server, but is accessed by multiple client devices. Okay, so one user, multiple applications for the client device, one application, multiple users, or clients in this case, for the server. That means that multiple client devices can take advantage of the extra performance capabilities and those economies of scale that come with that from the server, in the way that it would be completely pointless for you to download the whole catalogue of Netflix, say, onto your device. Why not? That is held on a server and multiple people can connect to that and stream down copies of that. Okay, so there we go. Now, servers come in a number or a couple of main different shapes and sizes, known as form factors. For smaller organizations, there are tower servers, much like a PC, and realistically, in a lot of ways, you can consider a server to be like a big PC, with the difference one application, multiple users, as opposed to multiple applications, single user. Now, a tower server is fine for a smaller organization, but if that organization were to grow and they would be using more and more servers, this takes up a lot of floor space, and as with servers, there's always lots of cabling, lots of tower servers on the floor, takes up a lot of space, a lot of cabling laying all around as well. So that's not ideal. So the form factor we use as for larger organizations is a rack server, this pizza box shape. Now you can have all the same components, those fundamental components of processor. You can have the same cores, the same amount of memory, and the same storage in here as you do in here, but it's just basically in a different shape, in a different form factor. But this rack server form factor means we can put it into, surprise, surprise, a rack. So a rack is like an electronic cupboard, if you like. We can put servers, pile servers up here, and so we can get a whole load of servers within there, utilizing just the single floor space of this. And we can then get a lot more servers into a room because we can have a lot more number of racks filled with servers. And the cabling all can be put neatly down the side and across the back there. Neatly, or sometimes not so neatly. But it's a lot neater than this approach, tower approach, and uses a lot less space. Okay, moving on. Where do servers go? Well, one of the places that servers goes is here in the cloud. What is the cloud? The cloud is basically someone else's problem. So, as opposed to a company having servers and racks on their own premises, on-prem as we call it, where they've then got to power those servers, cool those servers, because they run very hot, just like your laptop or your phone. If you're doing lots of stuff on it, it runs hot. Well, a server most definitely runs hot, and that will also need air conditioning in whatever room it's in to keep it at a steady, usually 34 degrees Celsius. So, another way of doing that, as opposed to having it on premise, is to have it use someone else's servers. Someone else has servers in their own data center, and you just rent the usage of those servers, or even part of that. You would rent a certain amount of operations per month, some sort of setup like that. So you're not having to buy the hardware, you're not having to maintain the hardware, you're not having to power the hardware, you're not having to cool the hardware. You are just using the hardware remotely, or using the applications remotely. Okay. Main companies dealing with this are Amazon with AWS, Microsoft and its Azure platform, and Google Cloud. Okay. Now, there can be a mixture of in the cloud and on-premise. So in the cloud, the public cloud, as we said, this is basically someone else's data center. As we see here, we've got huge room, lots and lots of racks, power, cabling. Across the top here, there's going to be air conditioning all through here. So it would be a mixture of using that and an on-premise server room. This could be example B. This is an extreme example, obviously, but say a small primary school or something like that just has a couple of servers, tower servers, one is stuck on top of the other. The IT manager, who also teaches PE after lunch, that's his lunch, sat there. A joke, obviously, but this gives an example. So you can have, say, like the organization. In fact, let's take a more serious look at this, which would be here. So we've got a data center here, private cloud, and we could say be running certain applications in the cloud. Lots of organizations run Microsoft 365. So that is using email, spreadsheets, Microsoft Teams, Microsoft OneDrive, all sitting on a Microsoft data center, but that company also has their own small server room with a few racks of servers where they would say be running the company website, the company's CRM, that sort of thing. So it's a bit of a mix and match. Reason for that would be, you can run all of these things here. You can run the website and the CRM in the public cloud. So getting someone else to do it, they provide all the infrastructure and whatever, and they host your applications on there. But that can be more expensive. There can be compliance reasons, meaning an organization wants to or needs to keep responsibility for their own data. So they would need to own the hardware that data is on, because let's face it, with the public cloud, you don't know what hardware your applications or data is on, or even where it is. Okay? So that would be an argument for having your own server room within the company. But again, for this, not only are you having to buy the hardware, but you're having to power it, you're having to cool it with air conditioning, and you are having to maintain that hardware. There is a third way of doing this, which is co-location or colo, which is whereby you would be owning your equipment, but that is being hosted in a data center. Example of a co-location company would be Equinix, and Equinix would charge you basically rent to site your servers in their data center. You would then pay Equinix for the connections, the power and the cooling, and you would either come along and maintain that hardware yourself if you were the company, or you would pay a professional services company to do that. Right. Another way of doing it is via a managed service provider, also known as an MSP. Similar to a co-location provider, except that the MSP looks after the hardware as well. So it remains the customer company's hardware. They still own it, but everything else is taken care of by the MSP. So it depends on going from public cloud through to on-prem, the different levels, how much you want to own as a customer, how much you want to maintain, and how much you want to keep under your own personal control. Okay. So with servers, there are a number of problems that the customer has, which dictates when and or how often they will need to update the servers. And the problems that you can talk about with your customer are pretty similar to those of your own smartphone. So with each year a new smartphone version comes out, a year or two, and it's going to have a better processor. So after a few years, the performance of that phone degrades, because with newer, faster processors, more cores, more gigahertz, whatever, applications are always being written for the latest and greatest processors, which means after a few years your phone isn't working as well with those applications, and it will need to be upgraded. Same thing with servers. Capacity as well. There's only a certain amount of storage that can be fit within a server, and when you buy a phone, it comes with a certain amount of storage, and when that storage is full, what are you going to do? You need to get either in terms of a server, more storage, or if that is full, like with the phone, you will need to upgrade that device. And then there are things like software updates. So a phone, or rather a server, is only going to be supported for a certain period of time, meaning the company is only going to be bringing out software updates for that server for a certain period of time. It's only going to be supported for a certain period of time, because the technology has moved on and they're working on developments and updates always for the latest device. So after a certain period, 5 years, something like that, it will no longer be supported, meaning if there's a problem, then you're not going to be able to rapidly get a replacement part. And for servers, infrastructure, the beating heart of the organization, typically the IT infrastructure, being able to get replacement parts rapidly is essential. So, all reasons why your customer will be looking regularly to update their servers. So it's always just a matter of speaking to them, understanding how often they update them, what their experiences are of updates, good and bad, which dictates when they're likely to do those refreshes, how frequently. But always remember, because we are typically getting more performance out of the latest processors, and those processors are becoming more and more efficient, that means that if you're going to have more cores on a newer processor, say you can have 128 cores on the new processors that the company buys, as opposed to 24 cores on their old processors. Well, arguably they're going to be only going to need a fifth of the number of servers when they upgrade than the number they bought last time. So they're going to be cheaper to upgrade, and it's going to be a lot more power efficient as well to do the same amount of work. Lots of reasons for regularly upgrading those servers. So that's servers. I want to move on now to storage. We've already spoken about storage in terms of being within the server, and this is called direct attached storage or local storage. Direct attached meaning that it is directly attached to that server. But as well as just being physically within the server, we can have another form of direct attached storage, which would just be having extra drive shelves in a container to store additional drives, additional hard disk drives or additional SSDs. There's no intelligence in there. Where and how to put the data is all done by the intelligence within the computer, the processors within the computer, within the server rather. Okay, that's good. So that means once the capacity of your server is full, you can still carry on adding data to it. But that has a limitation. And it's got a limitation because of the lack of intelligence within here. It means that if you've got two servers, both of those servers can have extra data, but there isn't a means of communicating between those different servers, and that could be necessary because let's say that these servers, this is an email server, or rather, sorry, no, this is the website server, and this is a secondary copy of that website server, because if that server fails, they can immediately have everyone connecting to this one instead. But the data that is used for that server is going to be the same data that is used for that server. So we've basically got two lots of the same server. But because this doesn't have intelligence, and intelligence is in here, we're not actually able to connect from that one to that one. So it's a lot of waste. And also, if we consider things like the website and your company CRM, well, that's using a lot of the same data. So as opposed to having lots of different copies of the same data not being able to be utilized by different servers, it makes a lot more sense to do something called, if we're going to be scaling out this organization, to use something called shared storage. Shared storage is where we have multiple servers, but they all connect to a central shared storage. So typically these individual servers in this arrangement won't have much in the way of storage in here. They won't have a lot of storage like in here. You would just have a couple of drives, probably to hold the operating system and maybe an application, but all of the storage that is used for, other than that, all of the storage that's used for all of these servers is held centrally in something called a storage array. So, what is the difference between a storage array and this arrangement, where you've got the storage here just in drives? Remember, in these shelves there's no intelligence. This storage array is essentially, well, it is a server, but it is a server that has one job: to look after all the storage for these, all the data for these other servers. So it has various things to reduce down the amount of duplication so you can get more data onto it. It has more advanced ways of keeping the data safe, known as RAID. It's a lot more efficient, potent at doing its task. So we can have things like data reduction. So we're able to reduce down the data, typically on a lot of servers, on a lot of storage devices these days, because there is a lot of duplication between data in applications. We can have a data reduction ratio of about 4:1, meaning there's a lot of duplicated data that is created by all these different applications. We keep just a couple of copies of it. We're not having to keep lots of it. So as opposed to having 20 terabytes, we can be using just 4 terabytes, say. But in order to find those duplications, that takes a lot of processing power. So this is why it's done on this standalone storage array. Standalone storage array, also called a SAN. You'll hear storage array or SAN. That is basically a shared storage. Shared storage, which means one intelligently run server dedicated to storing data on behalf of multiple application servers. You may be familiar with some of the storage arrays or SANs from Dell and HPE. We have here, so at the entry level, Dell's PowerVault ME5 or MSA. These are entry level arrays, and they don't have any of that data reduction I was talking about. But then these, the Unity or Electra 5000 or the PowerStore and Electra MP, really the flagships of HPE and Dell's mid-range storage portfolios. These have that data reduction on there. So they cost more, but they're more efficient, they're more powerful, they're going to be able to scale higher. So that is storage arrays. And what problems are we looking to talk about with the customer when it comes to storage arrays? Well, we kind of have more of our eggs in one basket. We have backup, which we're going to be talking about next time, but for our production storage, it tends to be sat more in one place. So reliability is absolutely essential. So again, the older a device is, when it's going to be coming out of support, that's a no-no, because we need to be able to upgrade. So we always have the best performing storage, because we need to be able to get data to the servers quickly, and it also needs to be covered. It needs to be supported. So if there are any problems, we can get replacements quickly. But there's also complexity as well, because the more data that we store as an organization, the more complex that is going to be placing it in the right way, keeping it secure, making sure that it is always accessible, and we just know what is going on. So there's for each new version of for every new storage product that a manufacturer brings out, there are more advanced management features to help operate under the increased complexity of greater data. So reliability, complexity, those are the main things you want to be talking about with your customer. Now, that's it for this video. Next time we will be talking about virtualization. You might have heard of VMware or Microsoft's Hyper-V. We'll be talking about that, virtualization. Hyper-converged infrastructure, which is a different way of going about putting together your servers and storage. And we will also look at backup, which is the way of increasing reliability even further. But that's next time. Thank you very much. Goodbye.